Hi, this is Algebra 1, Lesson 8-4, Modeling with Quadratic Functions. In this lesson, we'll be able to use quadratic functions to model real-world situations. Lesson vocabularies are quadratic regression and vertical motion model. Let's start with model and discuss. The graphic shows the height of a supply package dropped from a helicopter hovering above the ground. Would a linear function be a good model for the data? Explain. So if you look at the heights, we have 350, 335, 283, 206, 96 above the ground, right? It's going to hover above the ground, which means it's not just going to stay in the same position. It's probably move around, right? So would a linear function be a good model? Maybe if we know the helicopter moves in a constant height, like in a constant speed to increase or decrease the height, but it's not necessarily gonna move in a constant speed, right? In terms of height. So would a quadratic function be a good model then? Yeah. It would be a better model than a linear function, right? So let's write that down. So part A, we can say no, a linear function would not be a good model for the data, because if you plot the given data, the points do not appear to stay close to a line. 0 second, 330, 1 second, 335, 2 second, 283, 3 second, 206, 4 second, 96. Yeah, it doesn't have to be a linear line, okay? Would quadratic function be better? Yes, it would be better because when you graph it, it's going to go in a curve, parabolic, instead of a linear line. Okay, so yes, quadratic function would be a better model. If you look at the graph and you if you label all the points, you can see that it is not a straight line, it's closer to a curve, right? So it looks like a parabola opening towards facing downwards. So it's better to be plotted as a quadratic function instead of a linear function. Okay, so essential question. What kinds of real-world situations can be modeled by quadratic functions? Let's look at example 1. Use quadratic functions to model area. A company offers rectangular pool sizes with dimensions as shown. Each pool includes a deck around it. If Carolina wants a 15 feet wide pool with a deck, how many square feet will she need to have available in her yard? Write a quadratic function to represent the area of the pool and deck first so that we can solve for it. So if you look at the given information, we have a pool here, but then we have a deck around it, right? And the width of that is 4 feet. And then the width of the pool itself is x, the length is 2x, right? We want to know how many square feet will she need to have available in her yard if she wants a 15 feet wide pool with a deck. So first, 2x plus 4 plus 4 represents our length for the entire thing, right? So this entire thing, 2x plus 8, okay? And then if we look at the width, this entire thing should be 4 plus x, right? So x plus 8 represents the width of the entire thing. So the width and the length times, if you multiply the width and the length, that would be the area. So you can let x represent the width of the pool and write this expression to have have it as a function. So the quadratic function, 2x squared, if you multiply them out using the FOIL method, 2x squared plus 24x plus 64 can be used to find the area of the rectangular pool and the deck all together. And then we're going to find the area of the pool and the deck when x is 15 feet wide pool. So if it says 15 feet long pool, then we are going to use substitute that into the length, the entire length. But it's 15 feet wide, which means it's going to represent the width. So you can just plug that into x because x represents the width, right? So you're going to substitute 15 for x in your equation and see what that equals to. So she needs 874 feet squared to build a 15 feet wide pool with deck all together. That's what we wanted to figure out. So if you use the equation when you have an unknown variable and figure out using the information, you can easily figure that out. So let's look at try number 1. Suppose the length of the pool in example 1 is 3 times the width. Try number 1. How does the function that represents the combined area of the pool and the deck change? So the length is changing. And so instead of 2x, it's 3x. Okay? So your width is the same. Your length is 3x. So how does that change? Pause the video. Come back when you're ready for answers. Okay, are you ready? So how does that change the function? Instead of 2x, you simply put 3x, right? So your f of x is going to be 3x plus 8 instead of 2x plus 8. And you're going to multiply with the same thing because everything stays the same. It's just your length that's going to change. So you multiply that out again, use the FOIL method, 3x times x is 3x squared, 3x times 8 is 24, 8 times x is going to be 8x, and then 8 times 8 is 64. So you combine like terms and you have 32x plus 64, right? So that's your new equation, and plug in 15 for the area. So f of 15 is going to be 3 times 15 squared plus 32 times 15 plus 64, which will be equal to 630 plus 480 plus 64. And if you add all that, you will get 1,174. So she needs 1,174 feet square to build a 15 feet wide pool with a deck where the length is 3x. The length of the pool is 3x instead of 2x. So the expanded form would be this, but you're gonna that's because you replaced 3 instead of 2. Okay? So let's say the expanded form, I'm gonna scroll down so you can see. The expanded form of the function is f of x equals 3x squared plus 32x plus 64. Okay, and she will need 1,174 feet square to build a 15 feet wide pool with deck. Okay, let's look at the next page. We have a concept, vertical motion model. The equation h of t equals negative 6t squared plus v sub 0t plus h sub 0 is the vertical motion model. So write that down in your notes. The variable h represents the height of an object in feet, t seconds after it is launched into the air. So we have two variables here where t represents time and h represents the height. So over time, the height is gonna be different. It's gonna change. The term v sub 0 is the object's initial velocity. So velocity is kind of like speed. And h sub 0 is its initial height. Okay? So let's look at example 2. Keep that in mind. Model vertical motion. A diver jumps off a high platform at an initial vertical velocity of 16 feet per second. What quadratic function represents the height h of the diver after t seconds of the dive? We're going to use the vertical model to write the quadratic function. So use the model here, negative 16t squared. So negative 16 will not change, okay? Whatever your initial velocity is and your initial height is, you just plug it in into the equation, and that would be your vertical motion model, okay? So this takes into account the force of gravity, and so your height in the real world will follow this curve, okay? So your initial velocity is 16, so plug in 16 in for the v sub 0, and plug in the height 30 into h sub 0, okay? I think the picture is cropped, but if you look at your textbook, it will give you that the height is 30 feet in the diver's picture. So plug that in. And part B, how many feet above the platform will the diver be at the highest point of his dive? So remember your equation for your y value in your standard form. So x equals negative b over 2a was your equation, right? In this case, you have a form where your a is negative 16 and your b is your initial vertical velocity. So your vertical velocity is 16, your b is 16, and your a is negative 16. So if you plug that in into your equation, instead of x, we're using t. So you have t is equal to negative b over 2a. Plug it in, you'll get positive 1 over 2. And that will be your x value. So you need to figure out the height using your x, because that would be your vertex, right? Which is going to be at your highest point. So your x represents the time, but we want the maximum height, which means we want to figure out the value of y instead of x. But why do we figure out x first? So that we can figure out the value of y of your vertex. So once you figure out the value of t, you're going to plug that in into your equation. In this vertical velocity model, your x is t and your y is h, okay? So your h of 1 over 2, which is your value of t for your vertex, is equal to negative 16 times 1 over 2 squared plus 16 times 1 over 2 plus 30. So if you solve for that, that's negative 16 divided by 4 plus 16 divided by 2, 8 plus 30, so that's 34. So your vertex is 1/2, 34, which means your height is at your maximum at 0.5 seconds, where the height is 34 feet. Okay, so the platform is at a height of 30 feet and the vertex is at 34 feet. So the diver will be about 34 minus 30, or 4 feet above the platform. Because if that's your platform and that is already 30 feet above the ground, that means your diver will dive 4 feet. This is your maximum height, right? And that's 34 feet above the ground. And so it's going to be 4 feet above the platform. Does that make sense? Yeah, okay, let's look at try number 2. Now you're going to find the diver's maximum height above the water if he dives from a 20 feet platform with an initial velocity of 8 feet per second. So you need to figure out what this information means and where it goes. What does it represent in the equation and where does it go? Where do the numbers go? Plug it in and you'll be able to figure out yourself. So pause the video and see if you can figure it by yourself. Come back when you're ready for answers. Okay, are you ready? So what's our new equation using the initial velocity and the height, the initial height? So your height of the platform will be your initial height, right? So height of the platform goes here, h of sub 0, and then vertical velocity, initial vertical velocity goes here in the model. So you're going to write a new equation. H of t is equal to 16t squared plus your initial vertical velocity, which is 8 feet per second times t, plus your initial height, which is the height of the platform, 20. So that should be your new equation, okay? Your new vertical motion model. And then you're going to solve that. You're going to find the diver's maximum height above the water if he dives from that. So figure out the vertex of this equation. First, we want to figure out the x value. X value could be figured out by using this equation, t equals negative b over 2a. Because that's where your axis of symmetry is going to be and where your vertex is going to lie, right? And so your b is going to be, your new b is going to be 8, and your a is still 16. So then, simplify that equation, that fraction, and you have negative 1 over 4. So that would be your t of your vertex. And now with your new x and y, h and t, your t and h, your vertex will be t comma h, right? So you figured out the domain, okay, of the vertex. You figured out the x value, the domain value of t. And now you're going to figure out the value of h using your value of t of the vertex. Negative 1 over 4 is equal to 16 times negative 1 over 4 squared plus 8 times negative 1 over 4 plus 20. So 16 times negative 1 over 4 times negative 1 over 4 is positive 1 over 16. And then plus, that's negative, so it's actually going to be minus 8 divided by 4 is 2 plus 20. 16 divided by 16 is 1. So 1 minus 2 plus 20 would be our height. So 20 plus 1, 21 minus 2 is 19. So our vertex is going to be negative 1 over 4, comma 19. So that is your initial velocity. Wait. Yeah. Wait, your a is negative, so sorry. So that is actually negative, so that makes this positive. I'm like, this shouldn't be negative. So yes, that is positive, but your height is still, no. So that would make it positive 2, so positive 2. So instead of 19, 20 plus 2 plus 1 is 23. 20 plus 2, wait, let's do that again. 4/4, 1/16, that's 2, yeah. Yeah, so sorry. So that's going to be negative, negative, because A is negative. Yeah. Then that makes it different. So it's actually 20 plus 2 minus 1. So it's 21. Yeah, this is correct. So your vertex is going to be 1/4, comma 21. And now we can say that the diver's maximum height above the water would be 21 feet above the water. There we go. Yeah. So just remember that your A is always negative 16. Okay. That should be correct. Now let's move on to example 3. Assess the fit of a function by analyzing residuals. Each year for the past 5 years, ticket prices for a school play have increased by $1. The director used the function f of x is equal to negative 7x squared plus 90x plus 750 to represent the relationship between the number of price increases and the average predicted revenue per show shown in the table. How well does the function represent the actual revenue data? So, do you know what revenue is? So first of all, revenue is the amount of money you earn as a whole. Okay, and then let's see, what else do we need to know? I think that's all. So first, you're gonna use the function to find the predicted values for each price increase. So this function represents relationship between number of price increases and the average predicted revenue. So these are the two variables. One variable represents number of price increase. Okay, that's x. And then another variable represents the average predicted revenue per show. Predicted revenue per show. So that's f of x. You see that? So those are the x and y represent the relationship they're the variables that are involved in the relationship shown in the equation. So we want to know how well this function represents the actual revenue data. So let's look at the function and find the predicted values for each price increase. So if the price increase is $1, you plug in 1 here, 1 squared minus 7, then 90 times 1, 90 plus 750. If you add them, it's just 750. It's just 833. So you have 1,833, right? But then you look at the actual revenue here. These are the actual revenue that happened for real. But we have a model that has predictions, okay? So using this model and comparing these numbers, are the numbers pretty close or are they not even close? We're going to determine using the residual. The residual is how far off the prediction was compared to the actual point, actual data. So in order to figure out the residual equation is your actual value minus your predicted value. Okay? So 745 minus 750 is minus 5. So residual is minus 5. The actual value, 846 minus the predicted value, 833, is plus 13. So it's plus 13. So we predicted more on the second point, and then we predicted less on the first point, and then we predicted 8 more on the third point. We predicted 5 less on the fourth point, and then the last one we predicted 10 more. So then we can add all the residual to see, oh, is it close to 0? Because if it balances it out, that's how we can say, oh, it does. That's how we can compare how well the function represents actual revenue. So you can make a scatter plot. The scatter plot will not exactly fall into the curve, just like the scatter plot on a linear equation, right? You're gonna graph the function and then see if it does follow. Okay, the residual plot we have is here. So 0, -5, 1, 13. We're going to use the same x, but for each price increase, those are the predictions that we made. Those are how much the predictions were off. Okay, and then you're going to assess and say, oh, the residual plot shows both positive and negative, which is generally a good model. If it generally predicts a lot more, then it probably is not accurate. You might have to move the graph a little bit lower, right? Or if it consistently predicts a lot lower than your actual, then there's a better graph for that. But if it's both but if it has both positive and negative residuals, it means, yeah, the actual data were off, but off from our predictions, but our prediction kind of averages it, and it kind of shows the pattern. The actual data shows the pattern that are similar to our function, so then we can say it's generally a good model. Okay? So this is when we can say, yeah, it's a good model. So you're going to look at the residual. So let's look at try number 3. Make a scatter plot of the data and graph the function of this one. You're going to make the residual plot and describe how well the function fits the data. So this is the actual sales, okay? And then you're going to graph this function and see how well it graphs, it makes the prediction. So see if you can follow example 3 and figure out the residuals by yourself and come back when you're ready for answers. Okay, are you ready? All right, so if you graph it, I'm gonna use the graphing calculator online, but you need to be able to graph it by yourself, okay? So if you graph it, graph the function, you'll see a parabola like that. And if you plot the points, you will see these points here. And look at the residuals. So when x is equal to 4, it's 997 on the graph, but your actual was actually 1010. So actual minus 997 would be 13. So the residual is 13 here. So that's a positive residual. That's a negative. That's a positive. That's a negative. And then that's a positive. And that's a negative. So we have both the positive and the negative residuals. So we can say it is generally a good model. Okay? If it only shows all positive or all negative, then it's not a good model. So let's write that down. Okay, so here you can see the graph, my table of residual point. So you can subtract actual point minus your point on the graph. And these are your points for your residual plot. So the residual plot shows both positive and negative residuals, which means it indicates the function f is generally a good model. Okay, let's look at example 4. That would be our last example. Fit a quadratic function to data. The theater director at a high school wants to find the most accurate quadratic model for ticket sales based on the data in example 3. How would the revenue be affected if the prices increase one more time? So it's going to increase one more time. Quadratic regression is another vocabulary, is a method used to find a quadratic function that best fits a data set. So if you remember the best fit line in your linear equation, you have to use your graphing calculator to figure out the best fit line. Okay, you can also do that for a quadratic equation. So for this one, yes, you can use a calculator. Allowed. So using your function, which was negative 7x squared plus 90x plus 750. You're going to graph it and then find the best fit line in the quadratic regression feature. Yeah, your a is negative 8, and then that's all your coefficients. So in the quadratic regression in your graphing calculator, you will put in the values for the coefficients, and then it'll calculate your r squared for you. The function is a good model of a relationship because the closer it gets to 1, if your r squared is close to 1, it is good data. It's a strong relationship. So negative 1 or 1 shows, so if it's closer to 1, it shows a strong positive correlation. If it's closer to negative 1, it shows strong negative correlation. But if it's closer to 0, then it's weak correlation. So it's not a good graph, okay? So you can graph it as well. You'll see where the graph starts and then where it hits the highest point and then it goes down. So if the price of a ticket increases to 10, the predicted revenue will be $1,025.8. So let's look at try number 4, and we could do this by we could do this together. Use the model in example 4 to determine the predicted revenue after 6th and 7th price increases. So we're just going to plug in 6 and 7 into the equation. So what is f of 6 and what is f of 7? And if you simply plug it in, you'll figure out that f of 6 is $1,033 and f of 7 is $1,024.2. So you'll see that the revenue is decreasing, right? So you can say the revenue has started to decrease. So in order to get the maximum profit or the revenue, you want to stop at some point. You don't want to keep raising the prices. Otherwise, people will not buy. They will stop buying it and spending money for it because it's not, I guess, worth the price. So then your revenue will drop. So that is a good model to show where you can stop raising the prices. Okay, good. Now let's look at the summary. Modeling with quadratic functions is what we've learned in this lesson. So if you look at area, you have expressions for the dimensions. Use that to write a function. We have a vertical motion. So h of t is equal to negative 16t squared plus the initial velocity times t plus the initial height. So use this model to model vertical motion examples. And then for other datas, you will use residuals in order to see and compare if the graph is generally a good model or not. So residual is figured out by using the actual data value minus the predicted value. Okay, so that was lesson 8-4, modeling with quadratic functions. Thanks for staying tuned. If you have any more questions, I'll be happy to help in class. Otherwise, we'll continue with the next lesson in the next video. Thanks. Bye.